Okay, hi everybody. This is the first lab in Module 7 where you're going to be digging into deconstructing DEMs, which means first you'll be constructing DEMs, downloading different DEM resolutions and types from the internet, and then you'll be building them, mosaicing them together. But then digging in, doing some research and kind of picking apart the differences between them, hopefully to help you understand how to use DEMs properly in your own research. The type of data can really impact the analysis that you're doing. This is a picture of aster data that's been released by Japan's Ministry of Economy, Trade and Industry and NASA. It's not current data necessarily, although it has been updated quite a bit since. It's a global 30-meter DEM, which is pretty unique and valuable kind of in and of itself, but it is filled with errors. And as you try and run surface tools across multiple tiles, you find a lot of errors that need to be corrected before you can work with this data properly. But for what it's worth, it's a pretty interesting data set. So this lab can feel a little bit redundant. You're going to go to Utah's AGRC, their GIS portal, and download 4 different DEM data sets. We're not having you do this for busy work. There's a reason to download 3 different data types, but 4 different resolutions. They're all built differently. They require different knowledge and skill sets to piece together. But once you have that information, we want you to create a couple of maps illustrating the differences in resolution. And that's to help you guys see file sizes and how that can impact the work that you do, plus resolvable surface features and how that can impact both your ability to display the data, but also the kinds of, or the quality of information that you can pull when you're doing surface process analyses. So you'll be, like I said, downloading different DEMs at different resolutions. And what I mean by that is you're going to pull a 2-meter LiDAR data set. You're only going to pull 2 tiles because it's pretty cumbersome and it would take you all day to download the LiDAR tiles that you would need for the whole watershed that you're going to work in. You're also going to pull a 5-meter autocorrelated DEM. This isn't LiDAR. It's called an autocorrelation process, and part of what we want you to do is do some research on that and figure out what that means, where the data comes from, and some of the problems that are inherent with data like that. Then you're going to be pulling 2 NED data sets that are created by the USGS at 2 different resolutions, 10-meter and 30-meter. And again, it's important to do this so that you can see the difference in resolution, both at large and small scales, but also to understand how these are generated, perhaps from each other, and how errors can be propagated here with that process. So downloading all the data and getting it compiled is one step. Step 2 is creating some maps to illustrate the differences in resolutions. Number 3 would be to dig in and really understand where this data comes from, and I'm going to talk about that in one second. This last point here, how resolution impacts cell values, I just want to mention what I mean by that really quick. What I'm really talking about, resolution is the size of each cell. Maybe it'll be easier to look at here. These are maps that people created last year, and I just wanted to show you some examples of how you could approach this. I really like this example here because the map maker really zoomed in close so that we can see the real resolution differences between the LiDAR and the 30-meter NED DEM. You can see how pixelated it gets here. Each one of these cells, remember, this is the resolution. This cell size is the resolution. So this is a 30-meter by 30-meter cell. This is a 2-meter by 2-meter cell. And why that's so important is when you're dealing with an elevation model, the elevation is an average value for each pixel. So if you were trying to look at a peak, for example, or the elevation of a ridge, and you're dealing with a 30 by 30 meter cell, you have a lot of elevations in that area that are going to bring the average down. So your elevations are skewed when you're dealing with large cell sizes like this. In a 2-meter, it's going to be a lot more accurate. You don't have as big of an area with elevations bringing that peak value down. Obviously, if you could survey a specific point and get an exact measurement for elevation and include that as an attribute, that would be the most accurate. But when you're dealing with rasters, it's just important to take that cell size into consideration to know how that can impact the value of the cell. Slopes are different. Slope, it's a maximum slope over the area of that cell based on the adjacent cells. So every cell value is calculated a different way. It's not always an average, and so it's an important thing to know about rasters. Both how the cell value is calculated and also how cell size can impact that that cell value, resolution. I think I said that right. So that's it for that. These are just some examples. Like I said, you're going to be pulling just a small area for LiDAR, so you could choose to compare that area at the other 3 resolutions. But again, I would argue that going even closer really helps illustrate the differences between these DEMs. For extra credit at the end of this lab, if you want to, it's not worth a lot, but it's more for your experience. If you want to learn how to take raw point LiDAR data, raw points, and create a DEM surface from raw LiDAR data. This is a really easy, straightforward process to go through. There's a couple of video tutorials. You can pull LiDAR raw point data from any part of the country that it's available for. I'm going to send you to opentopography.org, and you can check out their map and see what they've got. Yeah, it's pretty straightforward, but it's an interesting process, and you can just, take the time to do that if you want. It's not necessary, but it is a really interesting process and could be useful for your research. So for what to submit, I just wanted to lay this out for you because it does go beyond downloading DEMs and making a map. There's a component where I want you to do some research on your own. Just get on the net, on the interweb, and research some of these terms. Where you've hopefully been exposed to LiDAR in your readings and the lecture PowerPoints. But autocorrelation processes are different, and we probably don't cover them like we should. This is your opportunity to learn where autocorrelated DEMs come from and what that means. So when I ask you to kind of bullet point this information, I do mean keep it simple. Don't write me a term paper about this. But if you can kind of organize the differences between these 3 data sets and 4 resolutions based on where the data comes from, not the website that you're pulling it from, but the actual source of this data. So LiDAR versus the USGS NED, these are constructed very differently and are built very differently. And same with the autocorrelated, the 5-meter autocorrelated DEM. Dig into that. Figure out how it's generated and how this generation process can impact the kind of inherent error. I'll give you a hint that the autocorrelated DEMs have a lot of error kind of built into them, and you need to know that when you're using it. Also, precision and accuracy can lead to just uncertainty in the data, like we're talking about with resolutions. That can impact it, and it can sometimes be quantified. Other times, you just need to pick the data that's best for your research, depending on what you want to do. And then address the availability of this data, the cost, and the cost can be both that LiDAR is really expensive to gather, but also the file sizes can be considered a cost. The available data extent, LiDAR is pretty limited. The USGS, I think, has made NEDs available for just about everywhere. Just address these things very briefly in your write-up. Same with resolution, comparing the file sizes and what can be resolved and how that could impact your research. And that's it. Good luck with this one.